Okay, students, welcome to Easy BTech, your guide for BTech and beyond. It is an easy learning platform. My name is B. Manohar. The today's topic is effect of temperature of a diode. What happens to current and what happens to diode current and diode voltage? Either the current and voltages may vary or not. That we will see with respect to the temperature. Is it clear, students? How the temperature will depend, how the temperature will affect the diode current and diode voltage. That we will see here. Effect of temperature. Okay, now you can see the standard statement. You have to follow that. For every 10 degrees rise in temperature, for every 10 degrees rise in temperature, reverse saturation current increases by doubled. Or suppose initially you have 2 I naught at temperature 27 degrees centigrade. At 27 degrees centigrade, you have the reverse saturation current is 2 I naught. At 37 degrees centigrade, the temperature will vary to 10 degrees rise, becomes double, 4 I naught. So, like this. This is the statement. Next statement is the first statement you have to remember. And the second is for every 1 degree rise in temperature, reverse saturation current will increases by 7%. For every 1 degree rise in temperature, reverse saturation current will increases by 7%. Okay, now suppose we know that the equation I is equal to I naught, diode current equation, e power v by eta vt minus 1. This is the diode current equation. Now we may give, suppose in the examination, what happens as the temperature will increase. You have to find the current I for various. We know V is applied voltage. And eta is nothing but ideality factor. That is 1 for germanium, 2 for silicon. This is the case. And Vt is a thermal voltage, that is 26 millivolts. Now suppose temperature, now initially at 27 degrees centigrade, you have 4 I naught. This is a reverse saturation current. Now as temperature is increased for a silicon diode, temperature increased by 1 degree centigrade. That is 28 degree centigrade. Now what is the reverse saturation current? You may substitute that here, you will get it. That is 7 degrees increase, 4 I naught into 7 by 100. You will get 7 for the 28. It's 0.28. The total current is I naught plus 0.28. Totally we will get the I naught here is this I naught, 4 I naught. It will becomes 4.28. This is a temperature due to temperature effect. It means as the temperature increases by 1 degree centigrade, the current from 4 to 4.28, it is increasing in 1 degree centigrade. For example, like that you may write here and you may find out the current. Now you know I naught. You know I naught value and V value he may give in the problem. Initially what is the total current with respect to reverse saturation current 4 I naught, you have to substitute here. But when the temperature is changed 27 to 28, 4 can becomes 4.8. You have to substitute this value and the change you can see here. We know V is the applied voltage, ET is the silicon means 2, VT is a 26 millivolts, everything is here known. Okay students. The formula for this is, suppose here 27 degree centigrade, you have 4 I naught. What will be like 97 degree centigrade? What is the reverse saturation current? It is one of the gate question. Okay student, 97 degree centigrade. Now what is the formula? I of t is equal to I naught of t into 2 power t2 minus t1 by 10. This is the formula. This is the formula. Is it clear? Now at 97 degree centigrade you need it. That is I naught of t initial how much? 4 I naught. 4 I naught into 2 power T2. T2 is second temperature. 97 minus 27 by 10. Now you will get 4 I naught into 2 into 97, 27. 7. 10. 4 I naught into 2 power 7. 2 power 5, 32. 2 power 5 is 32. 664. 128. 128 into 4. You will get the resultant. Okay students, this you can understand here clearly. What happens for 27 degrees centigrade, if temperature is increased to 97 degrees centigrade, the reverse saturation current will affected more, then the current through the diode will increases. Now instead of 4 I naught you are getting 512 I naught, more reverse current. Now definitely I will change, diode I will also changes. This is the effect of temperature. Similarly, for 1 degree rise in temperature, 1 degree rise in temperature, diode cut-in voltage decreases by minus approximately minus 2.5 millivolts. 2.5 millivolts. For 1 degree rise in temperature, the cut-in voltage of the diode is decreases by 2.5 millivolts. Now you can see here, what you can see, diode VI characteristics. During the forward bias, how the forward bias characteristics? This is a forward bias character. It is IF, this is VF. Diode under forward bias. Now this we known as V gamma cut-in voltage. V gamma cut-in voltage is 0.7 volts. Now if temperature increases by 1 degree centigrade, then it will be minus 2.5 millivolts. So it will be like V cut-in voltage is equal to 0.7 minus 0.02, okay, 0.025 millivolts. This is the value. You can decrease, you will get the value. It may smooth this side. It means as the temperature increases, this cut-in voltage move. Cut-in voltage will move this side. This is the effect of temperature. Effect of temperature under forward and reverse bias also current, reverse current. In reverse bias, reverse current, reverse saturation current will increases. For every 10 degree rise in temperature, reverse saturation current increases by double or increases doubles. And for every 1 degree rise in temperature, reverse saturation current increases by 7%. For 1 degree rise in temperature, the cut-in voltage will decreases by 2.5 millivolts. These three statements you can remember now. Due to temperature, first in diode, reverse saturation current increases by increases diode reverse saturation current increases by 7% for a 1 degree rise in temperature. Next, for every 10 degrees rise in temperature, reverse saturation current will be doubled. This I naught will becomes 2 I naught. Next, for 1 degree rise in temperature, 1 degree rise in temperature. For 1 degree rise in temperature, the cut-in voltage of the diode decreases by minus 2.5 millivolts. It means due to temperature, these three parameters are affecting. This is the effect of temperature. Follow these three statements, students, and the formula, don't forget. If you want to calculate the reverse saturation current, the formula I naught of T is equal to I naught. It means at what temperature? Okay. I naught of T into 2 power T2 minus T1 by 10. This is the formula. This is the formula. These are four statements, 1, 2, 3 and 4. Where you have to remember these steps regarding the temperature. Okay students, now we will discuss the next topic, that is load line analysis. Load line analysis for the diode. Okay students, for a load line analysis, if you draw the structure, draw a diagram. It is a diode. This is a diode. Now if you want, write this equation applying KVL. We will write a VI is equal to voltage across the diode VD plus the current. In series the current is same, that current is ID into RL. ID. VI is equal to VD, voltage drop across the diode, that is VD, and voltage across V0, output voltage RL, that is we write as ID into RD. ID into RL means current in series same. Okay, that is. Now under forward bias characteristics, if you plot the graph, this is your forward current IF, this is a forward voltage VF. Okay students, what is the diode characteristics under forward bias? May get like this. Okay. Now from this equation, exert the point. If you want to write the current, to draw the DC load line analysis, DC load line. Now we have to point 2 points in current in terms of milliamperes, because in forward, in the previous lecture we have studied what is the current. In forward bias current is milliamperes, forward bias. In reverse bias current is either micro or nano. This is for germanium, this is for silicon. Now you can see here from this load line analysis, Vi in the y-axis, to find out the current, y-axis, now whatever this voltage, we will make the Vd 0. If Vd 0, what we will get? We will get Vi is equal to Id into RL. Okay. Now from this graph you can see here, Vi is equal to Vd plus Id into RL. To calculate this IF current in forward, the point load line, this is nothing but we will write, this point we will write as Vi into RL. Okay, Id, current through the diode, we can write from this. This is 0 because on this line, y-axis, there is no voltage. Voltage is 0 at this point. At the origin, voltage is 0 on this y-axis. We will write Vi is equal to Id RL. From this, if you want to write Id, you will write Id is equal to Vi by RL. Now this Vi by RL, this point. And to know the voltage across the x-axis, from this if you want to write Vi is equal to Vd, because in this current is 0, we will write Vi is equal to Vd. Now we will write here, we can plot a line in between this. Okay. This point, and this point is called as a, this line is called as a load line. And this point is one of the way to calculate the operating, and this point is known as operating point or Q point or Q point, operating point or Q point. This we will call as an IDQ, and this we will call as a VDQ. This is VI. This is a load line analysis. You can solve a problem on this man. Okay, students, this is about load line analysis of a diode, and the previous slides we have seen how the temperature will affect. Okay, students, I hope you understood.